Welcome to CDR Horizons, a new series from Open Air hosted by Charles and myself, Harsh, in which we engage leading researchers about novel carbon removal technologies and ideas they're developing. CDR Horizons will explore the future of removing carbon dioxide from the atmosphere, and we're excited to have you on this journey with us.
In this episode, we speak with Graham Andrews, a research professor at West Virginia University. We chat about carbon mineralization in basaltic rocks, and Graham shares about his focus on the geological sequestration opportunities in Ireland. If you're interested in following breaking carbon sequestration research, definitely like and subscribe to our channel for more content. And now, on to the show.
Okay, thanks everybody. So I want to talk today about how we can explore for new opportunities to mineralize CO2 in basalt lavas, made famous at the Carbfix project in Iceland, but to move beyond Iceland. So while Iceland's a great place to do this, obviously, there are lots of other places that have a similar geology that have potential to allow other countries and other regions to take part in this kind of CDR activity. The basic theory behind it, I know it's a busy slide, but on the left, you see this nice cartoon from Sandalov et al.'s mineralization for CDR report from 2021. We have a droplet of water which has CO2 dissolved into that. That forms carbonic acid, so the pH drops from being alkaline to being acidic. And we now have bicarbonate, carbonate, and some hydrogen, which is where the acid's coming from. And then you pass on to the lower row, and those two hydrogen ions dissolved in the water attack silicate minerals, which is what the rocks are made of. So in the example shown, it's Mg2SiO4, which is the mineral olivine, which is very popular for this kind of thing. And it's one of several important minerals in the rock type basalt. So the hydrogen attacks the olivine and the rest of the basaltic rock, and it liberates magnesium cations, so Mg2+, but also calcium 2+ and iron 2+. Those then bond onto the carbonate, which is also floating around in the water, and that gives you a pH swing, because that then returns the pH to being alkaline, and now you make a carbonate mineral. In this case, MgCO3, which is magnesite. So now you've taken the CO2 that was originally dissolved in the water, you've now bonded onto the magnesium, you form a solid, permanent mineral. So all basaltic rocks, which is any kind of igneous or volcanic rock that has a very large proportion of magnesium, calcium, and iron in it relative to silica and aluminum, will dissolve the same way in response to acidic water. And if you add CO2 to that acidic water, then you've got the right ingredients to precipitate carbonate minerals. It's a natural process. This happens all the time. It's a very rapid process, and it's very thermodynamically stable. The attraction between a carbonate ion and a magnesium ion, for example, is really, really strong, and it's the preferential chemical reaction. So I showed up in the top right, got a typical picture of a volcanic eruption. Those are basalt lavas in Iceland. So they erupt and they're glowing, red hot lava, and they cool to make this nice black rubbly lava. It's the surface of that material that will react with the CO2. And there's been a lot of geochemical studies that have looked at this fluid rock interaction process and this pH swing, led by papers, for example, by Volkers. And they've estimated that you can sequester 1 ton of CO2 with 9 or 10 tons of basaltic rock, which doesn't necessarily sound like a great balance, but we have almost unlimited access to basaltic rocks. So we're constantly erupting basaltic rocks at the surface of the Earth. So we have volcanoes like in Iceland and Hawaii, which are very active. But most importantly, there's basaltic rock forming at the ocean floor all the time. So actually, probably somewhere between 1/3 and 2/3 of the total Earth's surface is covered in basalt. So there's no shortage of it. To demonstrate that, we have a map from Sandalov et al. 2021 as well. We're focused on the purple rocks, which are the mafic rocks, basaltic rocks. And these are all of different ages, and they've actually taken out the very youngest stuff that would be forming in the middle of the oceans right now. So they're only showing basalt lavas that are maybe more than 1 billion years old. You can see how much of the continents are covered in these. I've highlighted the Deccan Traps in northwest India. There's the Carbfix site in Iceland in the North Atlantic. And then there's an important site in the Pacific Northwest of the United States at Wallula in Washington State, which is a Department of Energy test site. The picture on the left is taken near Wallula. These are an area called the Columbia River flood basalts. So it's along the Columbia River, Pacific Northwest. They're termed flood basalts because there's so much of them that they, sort of by analogy, they flooded the landscape. They inundated the landscape over time. And in this photograph, you can see at least 5 different lava flows, which are labeled. And they're separated by these layers I've labeled as basalt breccia. Everything there is basalt, so it's compositionally all the same material. It's the same magnesium, calcium, iron rich rock type that we like. The difference is in the morphology of the actual way the rock is put together. The lavas form cliffs, and they're very, very strong and hard. You can see that they've got lots of joints running through them. You've got classic Giant's Causeway or Devil's Postpile type vertical joints. They form these prominent cliffs, and they're horizontal sheets that stretch across the landscape. But between them, you have these layers called breccia. And that's made up of the same material that has been broken up into boulders and cobbles and pebbles. So that is a representative section of what was actually drilled by the Department of Energy at Wallula. And they actually injected CO2 into that as a test. Going back to the map quickly, the size of the circles that are shown, purple is the basaltic rocks we're interested in, green are ultramafic rocks, so those are even more magnesium rich. The size of those circles is an estimate of the total capacity in gigatons of CO2 that could be stored in those sites. You can see that there's no shortage of potential places. There's no shortage of potential capacity that's shown. What there is a shortage of actual pilot studies and eventually operating sites to do this. So there's enormous capacity, even just on land, without going into the oceans, to sequester CO2 in rocks. So the 2 pilots that have been done, Wallula is shown in the sort of top center. So it was done by the Pacific Northwest National Lab of the US Department of Energy. It ran for about 6 years, and it took CO2 from the adjacent paper pulp mill that was captured by CCS at the flue. They injected it to about 800 or 900 meters below surface, and they mineralized in excess of 90% of that in just over 2 years. That means that they've put 1,000 tons of CO2, dissolved it into water, they pumped it underground, and in somewhere between 24 and 36 months, that's actually mineralized to form permanent carbonate minerals. So it's not droplets of water with CO2 in it that are hanging around in the rock. This is now solid mineral that can't move. And in that time and since, it's been monitored and there's been no leakage of CO2 detected. The Carbfix project in Iceland that gets a lot of attention, rightly, the highly shady geothermal plant. It's been operating in different guises since 2012, averaging about 12,000 tons per year of CO2. And they inject to about 750 meters. They have injected more shallowly before that, so the depth can be adjusted. At that one site, they have an estimated capacity of 1/3 of a gigaton, and they're mineralizing between 60 and 90% in a 2 to 3 year period. And so before these 2 projects were done, it was estimated that mineralizing CO2 would be, even under the best circumstances, would be a decade or century long process. Again, at Carbfix, there's been no leakage detected, and famously, they've partnered with Climeworks, so the sort of first operating big pilot for a direct air capture system was set up there, and now Carbfix are expanding to other sites in Iceland. So if we look at the pros and cons of this approach, the pros, as we've shown, there's abundant available space. Another advantage is that these mafic rocks and the ultramafic rocks that were also on the map tend to not be good agricultural land, so they tend to comparatively have relatively low population densities and other uses on them. So this is not competing with prime populated agriculturally used areas. The drilling is relatively shallow. In both the pilots, they were injecting CO2 less than 1 kilometer. And that has big advantages because drilling is very expensive. The costs approximately go up exponentially with depth. So it's cheaper to explore and characterize the rocks. It's cheaper to physically drill boreholes. It's cheaper to pump CO2 and water down. It's cheaper to monitor those systems. You can have more shallow wells rather than a few really deep ones. And it's a scalable system because as you expand a development or a project, you can just drill more shallow holes rather than committing to one really, really deep hole. You have rapid mineralization, so that pretty much guarantees permanence. So if that gets factored into carbon pricing or into other considerations, there are worries that people have, like this is probably the best guarantee you can get of keeping CO2 down for well in excess of 1,000 years. We're probably talking millions of years. That has advantages that it minimizes your monitoring time and costs. It's not staying down, CO2 is not down there as a gaseous or as a fluid phase that could escape. It's very simple science and technology. It's independent of big oil, which I'll come to next. And it has minimal induced seismicity risk. So in areas where we store fluids at significant depth, 2, 3, 4 kilometers below the surface, pumping water to those depths has a big risk of inducing earthquakes, so man-made earthquakes from that process. That's different from fracking, but it can produce earthquakes that are damaging at the surface. Because we're only having to store CO2 at maybe 750 or maybe even 500 meters, we're not deep enough to induce any earthquakes. If we come to the cons, we're looking at an unconventional process. And this is where we come back to big oil. Being independent of big oil sort of cuts both ways. It's good on the pro side because we can't be accused of greenwashing, and there's no risk of either accidentally or deliberately extracting more oil and gas by storing CO2 in basalt, which is traditionally how CCS processes have worked in places like Texas, where they inject CO2. And since the 70s, they've been injecting CO2 underground, but it's primarily been as a way to increase or sustain oil and gas production. So being independent of big oil is good from that sort of environmental anti-greenwashing perspective. We're not going to get any oil and gas out. We're not using it as any kind of cover for doing that. However, on the con side, being independent of big oil means that we are in the sort of trying to store CO2 in the basalt world or anything other than in sedimentary rocks, where you might also get oil and gas. We are in a frontier exploration zone. We don't have anywhere near the level of high quality data that oil companies have from oil and gas regions of the world. And we don't have knowledge of the subsurface. So it's playing catch up. They also have huge advantages in terms of infrastructure. So right now, and quite possibly for the rest of this decade, certainly maybe well into the next decade, geological storage of CO2 is going to be dominated by storing CO2 in big sedimentary rock basins by or in conjunction with the big oil companies. They have massive head start, they have massive infrastructure, and they have a massive knowledge and talent base to do this from. Storing CO2 in any type of rock, but especially in basaltic rocks, is a thirsty process. So at Carbfix, it's averaging about 25 tons of water for 1 ton of dissolved CO2. But they are developing their first pilot that will use seawater, and they've had several experimental studies that demonstrated that normal seawater will work with that. This is potentially limited to where it could be done in the world. Price is always difficult to estimate, especially as a geologist. The estimated lifetime costs for Carbfix are about $5 to $10 per ton CO2. And that's just the storage cost. The projections are that this kind of process has higher short-term costs, mainly because of our lack of knowledge about the detailed geology in these areas, but we have lower medium and long-term costs because of the much cheaper monitoring, the much cheaper drilling, and the huge volumes that are available. Really, the way to address those cons is to have more pilots. Right, we're trying to do this based on 2 data points. So what I've been working at the moment, this is purely office-based desk study, is looking at the Antrim lavas of Northern Ireland, which is where I'm from originally. So in the top right, you can see Benevilla Mountain, and it's those grey layered rocks at the top. That's the Antrim, that's the edge of the Antrim lavas. They're a lot older than in Iceland, 65 million years old. The rocks in Iceland, where Carbfix are injecting, are about half to a quarter of a million years old. But they're ultimately part of the same geological system. These are compositionally almost identical to the same rocks in Iceland. The Antrim lavas are up to about 800 meters thick. They're locally buried by about 400 meters in permeable clay. So on the map on the left, where basalts are pink. So the Antrim lava group are those 2 different shades of pink. And the clays are shown in grey, labelled LNC for Lough Neagh clays. And it's this area around Lough Neagh, which is that sort of cross-shaped lake in the middle of the image, that we're most interested in. The black circles represent the thickness of the basalt, and those come from a small number of boreholes. So you can see we have, first of all, we have very little data, is the first thing. We've got a cluster of shallow boreholes in the southwest of the lake, and we've got a few much deeper boreholes in the east and the north of the lake. But compared to an area which has been explored for and actually produced oil and gas, this is very, very little data to work from. We know we have big thicknesses of basalt. It's sort of an added advantage that there's 400 meters of impermeable clay above it if people are worried about leakage. And in the Irish context, this is the only large, viable carbon storage target that's on land. Anything else is offshore. And specifically in the case of Ireland, anything offshore is almost equally frontier as well. So Ireland is not a big industrial economy, but it is, just like anywhere, it's a significant greenhouse gas and CO2 producer that it has to address. So there's just simply an issue of what can you do to store CO2. This is data that I've collected and I'm writing up right now from the literature on the Antrim Lava Group, starting in the top left. This is chemical suite. It's magnesium and calcium, which are two of the elements that we want to bond with carbonate. And starting with the two grey crosses, the large cross in the upper half of the graph is from Iceland, that's the Carbfix site, and the small cross in the lower left is Wallula in Washington State, and that represents the average rock compositions in those two pilot studies. And then all the coloured dots through the middle represent Antrim samples. So you can see that in terms of magnesium and calcium, two elements we care most about, that they plot right in the middle. So we have basically a comparative chemistry for what we want to work with. And then the color of those dots is representing nickel content, which is really the only heavy metal contaminant we might be worried about. And you can see there's only one or two dots that are really dark blue. Then in the lower left and lower center, we're looking at some of the physical properties of it. So I mentioned that the lavas are these thick, hard layers with some joints in them, and then they're separated by these basalt breccia layers that are made up of boulders and pebbles and cobbles of basalt. Those are the layers we want to inject into because they have much higher porosity, they have much higher permeability. We're going to pump water with CO2 dissolved into it into the rocks. So the water has to be able to flow from the well into the rocks away from the well. So you need to have a geology that allows that water to move away. So we want to have high porosity and permeability. Permeability is just how easily can the water flow away. With these graphs, you're seeing that the main things to take away from this are that there's a lot of variability. Porosity in the lower left has big ranges of values from 0 to 60 or maybe even 80%. So it's highly variable. And then the permeability, which comes from that, is highly variable as well. We have rocks in the same borehole in any one location. We have rocks that are very low porosity and low permeability. Those are probably the thick lavas that would make cliffs at the surface. And then we have layers in between those that have got very high porosity and permeability. And that's where water would flow. That's where we would look to inject. And then on the right, this complicated diagram is showing a variety of properties that are measured vertically down the borehole. So the colored blocks are the geology itself. So those are the different layers of basalt shown in shades of pink. And then each of the lines in black and red are these different properties. And if we focus on the ones in red, we can see things like porosity and calculated permeability. And the thing to take away from all of these lines is just how sawtooth they are. Right? Most of those lines are not smooth. They're very jagged. They're very sawtooth or sort of shark's mouth-like. That's showing this alternating pattern of layers that are low permeability and low porosity with layers that are high permeability and high porosity, which is exactly what we'd expect in these types of rocks, and that's what we want to see. So that's sort of as far as it's got in terms of a characterization. Where this is going is to sort of just to demonstrate that these ancient 65 million year old lavas in Northern Ireland actually have the right characteristics for storing CO2. So it doesn't take into account things like capturing CO2, transporting CO2, but what it's suggesting is that the rocks are right. They have high potential to cooperate and to work. They have the right chemistry to mineralize CO2 rapidly. And that if we integrate data like this, which only comes at the moment from one borehole, but if we integrate that with the other boreholes we do have available, then we can begin to build a 3D model for what the total capacity could be. But aside from looking at this just in Northern Ireland, which is one small part of one small island, we saw with the maps that basalt lavas are found all over the world, and often in much, much greater thicknesses than they are in Northern Ireland. So places like the Deccan Traps in western and northwestern India, they're in the region of 2 kilometers thick. And India is obviously an enormous country compared to Ireland, has a much larger economy, has a much larger industrial base. So it's a good potential that the Deccan Traps, which have a similar geology, have good potential for CO2 storage there. And it's also good options for places like Hawaii or other volcanic islands, which are made of basalt and are often densely populated and have point sources. And are maybe also really good, again, like Hawaii, for renewable energy and for direct air capture systems on mountains powered by renewable energy, for example. So this might never become the dominant way to store CO2 geologically, but it definitely has the opportunity to expand beyond Iceland and to be a scalable solution that's maybe better suited to places with smaller industrial bases and maybe more land pressure and without a history of oil and gas exploration. Okay, thank you.
Yeah, so I guess just to start, we usually like to ask people, what was your kind of personal journey into this field of like CDR? How did you kind of end up here?
So I'm a volcanologist, so I've always been studying rocks like these. But CDR became my COVID project, especially during lockdown, and using things like the OpenAir's various YouTube videos. And I'd visited the Carbfix site, a little museum there, and got really interested in the idea. And I was also looking for ways to diversify my research. So it all came together really nicely.
Awesome. And maybe diving a bit deeper, because there's so many people doing different types of mineralization. Would love to hear your thoughts. How do the different forms of mineralization stack together? Like, how does this compare to all the other storage options?
I like this because it's simple. The technology already exists, and it is not perfectly, but it is easily verifiable. And so I like this just because it's simple, it's straightforward, it's scalable, and it's a viable alternative. In many ways, it's a preferable alternative to storing CO2 underground in sedimentary rocks, which is it already is. It's going to be a industrial scale process. Like at the moment, that's the only way to conceivably get to gigaton scale CO2 storage. Right? There's obviously CDR has all kinds of potential, but at the moment, the only thing you could actually go to for millions of tons and potentially up to gigatons of storage is storing it in old oil and gas fields and in the associated rocks with those. That's going to be $1 billion industry, and it's going to be a very heavy industry, big scale, and it's going to be dominated by those same corporate powerhouses that have been extracting oil and gas for over a century. And regardless of how you feel about big oil or how you feel about big corporations being involved, there's an ethical and moral question there about should the companies that are producing oil and gas also be the companies that are storing CO2 at the same time. And that's not a sort of out there abstract philosophical concept. At the moment, they are the only game in town for storing significant volumes of CO2, and it's going to be that way for at least the next 5 to 10 years.
Mm-hmm. So you kind of talked about, like who's kind of out there, and you're saying it's just big oil and gas. But what are some steps we can take to kind of accelerate the deployment and capacity of these things? And like what are some concrete policy steps, perhaps, or who are some folks that you think could be entering this space that we're not seeing yet compared to the incumbents?
No, I think there's lots of positive movement on this. Even just in the last couple of days before this recording, National Energy Technology Lab of the U.S. Department of Energy just released a carbon mineralization specific call for proposals that falls into 3 categories, one of which is CO2 storage, and there's $45 million behind that. So if you look at where we are with CDR in the first half of 2022 and things like the X Prize, There's been lots of activity on in research and with startups on actual carbon capture, like massive progress there for direct air capture technologies in a host of different ways. So and to me, that's the fundamental issue. Like from a thermodynamic perspective, the hardest thing to do is get CO2 out of the atmosphere. It's easy to store CO2 when you have it. The hardest thing is to get it in the first place. So there's been huge progress there. There's obviously a lot of motion towards utilization of CO2. So things that are what we hear about all the time now, things like concrete, and maybe turning it into plastics and other materials. But getting those out of niche markets, getting those into mass production, where they're actually going to be locking away millions of tons to gigatons, that's a long way off to get to those scales. So we're making progress on capturing CO2. We're making progress on utilizing some or all of that CO2. But at the IPCC report sort of emphasizes that CDR and direct air capture in particular have to be key parts of preventing a climate emergency becoming a climate catastrophe. We need to be ramping up at a technological rate that's never been seen before to get to gigatons of removal. So the question will quickly become, if there's massive progress on the capture end, well, okay, where are you going to put it?
Yeah.
So we have lots of space, and those companies that are already burying CO2 will be happy to take that. They'll be happy to take money to pay to do that. I think this is an interesting place, and it's good to see that there's getting support from US federal government and increasing recognition from other sources that there are alternatives to ultimately paying oil and gas companies to put back CO2 that they helped bring out in the first place. And also that solution, and it's technologically a very good solution, that solution is not ideal everywhere. For the United States and Canada, it's a great solution. Right? It works really well. For many other parts of the world, India is one, massive economy, largest democracy in the world. South Africa, massive economy. Many parts of Brazil, places that come to mind straight away. That solution of storing storing CO2 in old oil and gas areas is not ideal. Right? It doesn't work. So given the power that DAC can effectively be deployed anywhere to capture from the atmosphere, whether it be direct like sort of machines, like a Climeworks system, or it's through some kind of BEC system or biotar system, or using biology to draw the CO2 out. This can be done anywhere. So it's, in that sense, it's a very equitable solution. So this gives hopefully a second pathway to storing CO2, maybe with a much smaller cost footprint and smaller environmental footprint as well. The problem is that we're dealing with mega corporations that have been doing this for 30 or 40 years. They have a big head start. So the capacity is there, and as they've shown with Carbfix, this can work very well. It doesn't have to be tied to geothermal. The Carbfix site just happens to be at a geothermal power plant, but geothermal power is not a necessity to do this. So this can be rolled out. It can be rolled in lots of places that other mechanisms can't. It could be really powerful in places like Hawaii and other volcanic islands, where you have lots of solar, lots of wind power, and you have lots of land that is not suitable for agriculture. Those could be ideal solutions for having major direct air capture systems set up in those places, for example.
And I guess I'm curious, right? Like as we scale and have more players entering, and it's really encouraging to hear the grant for 45 million and some of the other actions. The one question I'm sure a lot of our listeners would have is, like, how do we guarantee the permanence? And so I think, and you said like for the Iceland side, it's like 60 to 90% was mineralized within the first 2 years. Is that permanent, or is there still some leakage there? And then what about the other 30%?
So once it's mineralized into a solid mineral, it is permanent over geological time. The only two ways around that, if you wanted to take those minerals and get the CO2 out of them again, your two ways to do it would be to calcine it, so heat it up above 700 degrees centigrade, like you would to make limestone, or to make cement from limestone, or to soak it in a strong acid. And neither of those scenarios is likely to occur in any of these reservoirs. If you were to have a volcanic eruption like right next door, you might raise the temperature high enough for a very small proportion of what you'd already mineralized. But it would be tiny. And the volcanic eruption, frankly, would produce far more CO2 on its own than it would accidentally release from your reservoir. So once it's mineralized It's there. We have carbonate minerals that are billions of years old on Earth. There's no reason to think that anything that we sort of engineer or enhance the natural process here would be any different. And then in terms of the proportion that's mineralized, you have two things working in your favor. With time, you'll mineralize more and more and more. So eventually everything's mineralized. But say you're in the scenario where you've got 60% is mineralized in 2 years, which means there's 40% that's still CO2 dissolved in water. Well, that part it's locked off because the rest of it's cemented around it. So now you've got bubbles of water with CO2 in them, but they can't escape because the neighboring spaces have actually crystallized to make minerals. And then with time, they are going to grow as well. So especially over geological timescales of thousands to millions of years, you can't guarantee anything, but I think it's been demonstrated sufficiently that this is a process which is as close to a guaranteed zero leak scenario as is possible. I'd say, to be fair to the storing in sedimentary rocks scenarios, they're being stored at much greater depths. I see in lots of papers on this that people worry about leakage from those. Leakage is really not an issue. Leakage of CO2 from these geological stores of any type is really, really not an issue. And places like West Texas and Oklahoma, where they've been doing this for 40, nearly 50 years, the number of leaks that have come up is absolutely trivial. And the total volume that is leaked is trivial compared to the volumes that have been pumped down. There's a variety of explanations combined for why that happens, but it's really not a big problem. Leakage is not a significant issue, even though it's one of the first things that comes to everybody's mind.
That's awesome. Super encouraging. Charles, any questions on your end?
Yeah, I guess maybe just to close out a little bit and also to bring up some of the things you've been working on, how can open air, I guess, help as a community of policy activists and open source hobbyists who are working on CDR, particularly with like your Ireland push to focus more on the basalt there?
I think on the policy side, it'd be sort of emphasizing that there's different ways to do this geological storage, and that there are potential benefits to being independent of big oil and being independent of having to be part of a $1 billion infrastructure project. So for economies or regions sort of trying to dip a toe into this, that's quite a big commitment to enter into some kind of like 50-year, $1 billion agreement with a global corporation. This is potentially a way in that can be scaled, starting with a pilot project. Like that's what I would like to see for Antrim. I'd like to see in many other parts of the world. Like Hawaii would be a good one. These are the kind of places that pilot projects to allow us to study those rocks, to understand, can a pilot project be scaled up to industrial? So trying to get that message across. And then to the broader open air and CDR communities, it's that thing of, we obviously have a lot of work on the capture side and particularly on the utilization side. And that's where so much innovations come, but we really need innovation on the geological storage side as well. Because like I said, the technology that is being used is 40 or 50 years old. Like the science and technology is relatively simple. You dissolve CO2 into water, you pump it underground. You either pump it so deep that it can't escape, or you pump it shallow into rocks that it will react with. But innovation, even outside of the immediate field of CDR, innovation in terms of drilling technology, innovation in terms of transporting CO2. So anywhere people can see ways to think about how this builds together as an entire ecosystem. Obviously, people get in the weeds of what their expertise is and what they're focused in, whether it's capture or utilization. But if you think about it as an entire ecosystem, where what I'm talking about is the end of that, where we're burying it at the end, sort of making sure that there's not gaps in that ecosystem or gaps in that pipeline, where we really become great at capturing CO2, but then we now have so much CO2 we don't know what to do with it. Like that would be a good problem to have. But yeah, there's lots of room for innovation. But this technology, as it stands, is ready to go. Like I said, what we need is pilots, and that's the kind of thing. If you're working on a CDR technology where you're at the point where you're capturing CO2, or you're about to capture large quantities of CO2, like say kilotons, you're at that point where you want to have a pilot project, and sort of an industrial scale pilot project of your technology. What are you going to do with that CO2? Are you just going to store it in tanks on your site? Well, that's good for 6 months. What are you going to do 2 years from now? So thinking ahead of where are you going to put that CO2? Is there a concrete market to sell it to, for example? At some stage, you might be, you know what? I'm at the stage of I either have to release it back to the atmosphere, which sort of seems counterintuitive, or I've got to put it somewhere. So thinking ahead and talking with bureaucrats and with legislators and things like that about trying to build in that ecosystem of where to put the CO2 when we have it, because there is a solution that's there. We just need to roll it out too.
Awesome. Yeah. Well, thanks for providing that insight and for coming to us and sharing your work. Definitely look forward to seeing how it progresses. And yeah, thanks for coming on.
Yeah, thank you so much. Really appreciate this. And